now you are getting the new test data, it will assign it to a team which is totally different from what it should have assigned it to. So this is what would happen. Now, how do we handle the situation? Okay, so that is the, let's go back to, okay, so I have moved this further down here. So this is a little bit more of the background of why, while the problem is eminently doable, it doesn't work. So what do we need to do? So what we need to do is, this is what we need. We ultimately, these words which are part of the description, we need to have already trained them. So how do we need to have already trained them? Without any context to this particular problem, we know that these words are part of the English language. So they are not coming, they are not totally new words which have no connection with what we have seen in the past. These words are actually part of a vocabulary. We have a lot of existing corpus of literature, English literature, I mean. We have, for example, Shakespeare's works, maybe not Shakespeare because it's it's old English, but I'm just giving Shakespeare's works. We have the encyclopedia, maybe the Wikipedia, I don't know if the spelling is right. We have the Wikipedia contents, right? So we have a whole lot of contents where we have a lot of contextual English sentences. We have a lot of words which appear in sentences. So we have words not as discrete items, but as part of body of work where they have a context, they have a meaning, they have synonyms. So we can learn. I mean, it is like a human being learns vocabulary right from his childhood. Here, the machine is learning the words by looking at all these works in the literature, whether it is Shakespeare, whether it is encyclopedia, Wikipedia, I don't know, Leo Tolstoy, whatever else. So you have a whole corpus of literature. So what you do, you train the neural network. Now, I'm saying neural network because I know that is how word2vec works. But essentially, what you do is you train the network, you create an embedding of these words in a much smaller dimensional space where, if you go back, I showed you the, sorry, what did I do? I should undo it. Whatever I did, I undo. Let me undo it. Okay. If you see here, we need to do something like this, where the words like push and pull become close to each other, which are quite different from a word like boy. I mean, this is what we want to do because this has no context. This is not specific to the problem that we are trying to solve here. It is not like it's not specifically for the issue tracking tool. The issue tracking tool contains description which are in English language. So we want to use the fact that it is part of the English language to do a existing training. Okay. So what we do, let me explain that now. So the way we do it is, I'll give you the most naive example, naive way you do it. So let us say I have a set of words. So let me say I have, let's just write some sentence that I had bread and butter for breakfast. I'm just writing a random sentence. Okay. Now, this is just one sentence, but imagine that this is actually it is not just one sentence, but there is a whole series of words which are coming from sentences across the whole corpus of literature that I just mentioned, like Wikipedia or encyclopedia, all that. So now, the to explain how word2vec works, I'll split this sentence into bigrams. So what are the bigrams here? I had is one bigram. Had bread is the next bigram. Bread and is the third bigram. So these are all bigrams. So what I'm meaning by bigram is I'm taking all pairs, this and this, this and this, this and this, this and this. So these are all the bigrams. We construct all possible bigrams out of this corpus of literature. Now, bigram is because I wanted to be naive. I mean, in general, you would not do bigrams. You would actually do n-grams, where you pick maybe 5 words at a time, not 2 but 5. So you would have I had bread and butter would be one 5 gram. Then had bread and butter for would be the next 5 gram. So once we do this, we have constructed a whole lot of bigrams or n-grams in general, but let me start with bigrams because that makes the explanation a bit easy. So what we do is, we remember I already mentioned that we have the one hot encoding for each word, which means each word, if you look at the, let us say I have a input which is of size v, where v is the size of the vocabulary. So a given word will have only one of these nodes as 1, all others will be 0. So let us say we had, for example, the word I. For example, maybe the word I had was corresponding to the second word. So you had 0 here and 0 everywhere else. So each word would correspond to one of these nodes alone being fired with a 1 and all others being 0. And there are v being the size of the vocabulary. I'm just calling it v, the size of the vocabulary. So that many input nodes are there. So what we do in this neural network is we construct a hidden layer. So this is the word2vec construction. So word2vec construction, we have the input layer which consists of the number of nodes equal to the size of the vocabulary, and the hidden layer to be the reduced dimension, like while the input layer would have been 1,000,000 in my example that I gave earlier, the hidden layer would have been something like 500, which means we are bringing down this 1,000,000 dimensional vector to a 500 dimensional space. But in this 500 dimensional space, it would not be all independent. It would not be that, it would be the way I showed the push, pull and boy, you remember? So it would be that the values would be more continuous. It's a distributed representation. It is no longer this kind of one hot encoding. Okay, so you would have continuous values for the various vectors. Now how does it come? I'll explain it to you. So the hidden layer is going to be n equal to 500, and the output layer is once again going to be the same v, which is 1,000,000. Okay, so how does it work? So what we do is the input, if you look at this bigram, I was here. Now maybe the had was the 4th in this series that I have shown. So it would be 0, 0, 0, 1, 0, for example. So this means for this input I, this is the training data. In the training data, we have the corpus. So we actually feed in the input vector like this, and the output vector is the second part. So the input is the first part of the bigram, output is the second part of the bigram. And we have a whole such bigrams because in this corpus, which is a huge corpus, we have created zillions of such bigrams or zillions of n-grams. That I will explain a little later how n-grams happens, but bigram is easier conceptually. So what we do is we have this input and the corresponding output, and we have a fully connected layer, which means every node connects to every node here with a weight matrix W. So when you have a fully connected weight matrix between a v-dimensional space and a n-dimensional space, the matrix would be v cross n, obviously, right? So there is a matrix of weights where each input gets connected to the hidden layer, and from each of the hidden layers, again we have a fully connected layer. Again, there's going to be a, I will call it a W dash, and this will be a n cross v matrix, right? So you have a weight matrix here and a weight matrix here, and the interpretation is that when we whatever we finally we get as the weights, so what would happen is, if you have a vector v, which is the input vector is, let me symbolically write the input vector as w, there are too many w's, so let me write the input vector as vi, which is basically one of the words that has come through the first part of the bigram. And then you have the, symbolically you have the matrix. So the vi is a column vector which is n dimensional, right? Now it is going to get multiplied with a v cross n matrix. So when this happens, you are going to have an n dimensional vector. Let me confirm if I have, if v is a row vector of v dimensions and you are multiplying it with a matrix, so this is actually a 1 cross v into v cross n, so it would have become a 1 cross n matrix, correct? So 1 cross, this is the 1 cross v multiplying with a v cross n would have become a 1 cross n matrix, am I right? Yeah, so it would have become a 1 cross n matrix. Yes, so it would have become a 1 cross n row vector. So vi wv cross n, and then you do w dash n cross v. So what happens when you do this? Vi times w v cross n times w dash n cross v, you have one more matrix here. This is the v matrix, this is 1 cross v, this is v cross n, and then there is a n cross v. So you end up finally getting a 1 cross v matrix. So you end up getting another row vector. Now this row vector is interpreted, because ultimately we want only one of them to be triggered, right? Because whereas what would have happened if you had weights, you would have had, though this would have been all 0 and only one of them would have been 1, because you are having a matrix which is having values everywhere and a matrix which is having values everywhere, what you end up having here will be a vector which will have values at multiple places. So there will be a a1, a2 everywhere, right? So the av rather. So the way it is interpreted is, this is interpreted using the softmax, which means each value here is exponentiated. Okay, so what we do is, this is going through a, so let us say this was a matrix, this was a vector which I call it as a1 of all the way up to av. So the interpretation is, this gets converted to a probability using the softmax function. So it becomes e to the power of a1 by summation e to the power of ai, e to the power of a2 by summation e to the power of ai. So this is the softmax. So this vector gets converted to a vector of probabilities. These probabilities, if you add all the probabilities, you will of course get 1, because the denominator is the normalization factor, and you are doing the exponentiation to make sure that ultimately all the values are positive, because even if one of these is negative, e to the power of will make them all positive. So this is the, and you interpret the one which has the maximum probability is the one which you interpret as the word which is predicted by this network. Okay, so let me now